Right then, another video responding to a comment, this time asking to produce a video on applying the laws of thermodynamics in questions. So I'm just going to state the laws of thermodynamics, and then we're just going to do an example just to see how we can actually apply them. So we're going to start with the 0th law, which basically states that if you have two objects, A and B, that are in thermal equilibrium with each other, and a third object or system object C that is in thermal equilibrium with A, then that must mean B and C are also in thermal equilibrium. The first law states that the energy increase, the increase in internal energy of a system is equal to the heat energy supplied to it minus the work done by the system. So remember, this is an increase in internal energy. This is the heat transferred to the system, and this is the work done by the system. Okay, so in layman's terms, the energy you put in, the heat you put in, minus the work the system does, whatever's left over, that is the increase in internal energy of your system. The second law, different variations, but the change in entropy, so the entropy of any system always increases. In ideal systems, it remains the same, but it can never ever decrease. How we apply that in physics is we say that energy cannot flow from a cold region to a hot region spontaneously. You need, in order for heat engines to work, you need a source. So heat engines need a source and a sink in order to work. And then lastly, the third law just states that when the temperature reaches 0 Kelvin, the entropy of your system is 0. There is no motion, no energy, no nothing. Okay? How might we apply that in an A-level physics question? I've prepared some. I've taken this from a past paper, but you have to be careful with copyright stuff, so I've just typed it out. So question 1. The first law of thermodynamics can be expressed by the equation Q is equal to change in U plus W. State the meaning of each term in this equation. My version is slightly different, but it's just rearranged. So what is Q? Q is the energy transferred to the system. Delta U is the increase in internal energy of the system, and W is the work done by the system. So we are thinking about the system, right? If you transfer energy to a system, that is then split into the increase in internal energy of that system and the work done by the system. All we are doing with thermodynamics, thermo, you can think of it as heat or energy, dynamics is movement, the movement of energy. Where does energy come from? Where does it go? Is it conserved? Okay. So moving on to question 2, a system consists of a perfectly insulated room containing only an empty refrigerator. The refrigerator is connected to the mains electricity, and the refrigerator door is open. Deduce, by applying the first law of thermodynamics, whether the internal energy of the room increases, decreases, or stays the same. So this is an age-old thing. If you want to cool down a room, just open your refrigerator, but that may or may not heat up the room. We're about to find out. So Newton's first law. First law of thermodynamics, Q is equal to W plus delta U. What is happening? Well, remember what W is. We've just defined it as the work done by the system, but here the work is being done on the system. So W is negative because work is done on the system by your mains electricity and your refrigerator. So if W is negative, what is Q? Well, Q is 0 because you are in an insulated room, right? As a system, the heat supplied to it is 0, okay? So if your Q is 0, and that equals a negative number plus delta U, then delta U must be positive. Your internal energy of the room increases because work is being done on the system and the temperature, or the total heat energy is 0. So our delta U is positive, and therefore it must increase. Okay, so that's just applying Newton's first law. Newton's second law. Why am I keep talking about Newton? This is thermodynamics. Newton clearly lives rent-free in my head. Right, next question. One definition of an ideal heat engine is a device which provides the maximum possible output of work from a given input of energy by heat transfer. The figure below shows a heat engine that appears to agree with this definition. The engine takes in energy from a high temperature source and work is done by the engine. Question 3, complete the above figure so that the engine obeys the second law of thermodynamics. Remembering that entropy must increase, we know that energy cannot flow from a cold source to a hot source. We must have a cold sink in order for a heat engine to work. Question 4, explain why the maximum theoretical efficiency of an ideal heat engine must be less than 100%. So for a heat engine, our efficiency is given by the difference in temperature between your hot and cold sink divided by your temperature of your hot sink. Now, TC, so your temperature of your cold sink, cannot ever be 0. It cannot ever be at absolute 0. It must be greater than 0. Therefore, the difference in temperatures must be less than your hot temperature. And so if you're dividing a smaller number by a bigger number, our efficiency must be less than 1 and therefore less than 100%. Okay? So understanding Newton's the second law of thermodynamics, we can introduce, we must have a heat source, we must also have a cold sink in order for heat engines to work. I hope that helps. I can't, do loads and loads of examples of this. I'm quite short on time, but hopefully I've just increased your understanding of the laws of thermodynamics, the accounting system really of energy. If it comes in, it must go out. Where does it go? Where does it come from? Please let me know in the comments if there's any other videos you'd like me to make. I hope you're finding them useful, and I'll see you in the next one. Cheers.